Question number 37. We have a circuit like this, and we are given E1 is equal to 3 volt, E2 is equal to 2 volt, and E3 is equal to 1 volt, and R1, R2, R3 are all 1 ohm. Find the potential difference between points A and point B and current through each branch, this, and this. So one way to solve this equation is using Kirchhoff law in this loop and this loop, and then apply the fact that the current in any one of these branches will be equal to sum of these three branches. Because A and B, there is no external resistance. So for example, if I1 current flows this, then this will be equal to, and if we assume the current flowing this, then I1 will be equal to I2 plus I3 or something like that, then solve this thing. It is not too bad, but it will take some time. So we will use a trick, and that trick is to the parallel combination of a set of cells with internal resistance. And that rule says that if you have n cells, E1, E2, E3 have internal resistance R1, R2, R3, so on and so forth, then this whole thing can be replaced with a single cell with equivalent EMF E is given by sigma EI divided by RI, or E1 by R1 plus E2 by R2 plus E3 by R3 divided by sigma Ri 1 upon R1 or plus 1 upon R2 plus 1 upon R3.
Mom?
So in this case, E1 is 3 volt, E2 is 2 volt, E3 is 1 volt, R1, R2, R3 are 1 ohm. So we have 3 by 1 plus 2 by 1 plus 1 by 1 divided by 1 upon 1 plus 1 upon 1 plus 1 upon 1. 3 plus 2 plus 1 is 6, divided by 3 we have 2 volt. And the equivalent resistance, if R equivalent is the equivalent resistance, then 1 upon R equivalent is sigma 1 upon R equivalent, and we have 1 upon 1 plus 1 upon 1 plus 1 upon is equal to 3, and R equivalent will be 1 upon these 3. So we can replace the whole this thing with 2 volt battery that we calculated here and a resistance of 1/3 ohm. And we can find out the first answer is 2 volt. That will be the voltage across A and B. And then we can find out the current, this I1, as E1 minus with the rule, the voltage across A and B, we found that 2 volt. So the current in this one will be 3 volt minus 2 volt divided by the resistance R. And similarly I2, we know that this is 2 volt, the voltage across this is also 2 volt, so it's 2 minus 2 divided by 1. And finally in this one the current will be opposite direction. Let's understand a little bit about the current direction. This is higher volt, 3 volt. So this will overpower the current's other voltage, because other voltages are smaller. This is 1 volt, so the current will flow into it and not go out of it. And that's why this current I3 has come out to be negative. So we'll spend a little bit of time to derive this equation. And this is what I have: n parallel cells, E1, E2 up to En. And they have internal resistances R1, R2 up to Rn. If we assume that the voltage between points A and B is VAB, then we'll have VAB is equal to E1 minus I1 R1. And similarly, for the second branch, we can write VAB is equal to E2 minus I2 R2. And similarly, for the nth branch, we have EAB is equal to En minus Rn. Now these currents I1, I2 and In, all these things will combine and will give out a total current of I. And this total current I, because we have not connected anything across it, this current I is sum of these currents is going to be 0. And if we want, we can substitute the value of I from this equation. I1 is equal to E1 minus VAB divided by R1. And similarly, R2 is equal to E2, we take I2 R2 on the left hand side, we calculate E2 minus VAB divided by R2. And so on and so forth for the nth term, this is equal to 0. Now we put together all these E1 terms together and VAB terms together. We have E1 upon R1 plus E2 upon R2 plus E3 upon R3, so on and so forth, all of them in one place, and minus VAB upon R1 plus VAB upon R2, so on and so forth, VAB upon Rn is equal to 0. If we collect these two, VAB take common from all these things, we get VAB multiplied by 1 upon R1 plus 1 upon R2 plus 1 upon R1 equal to E1 upon R1, E2 upon R2, En upon R1. Now these terms we simplify and write it as sigma EI divided by Ri, as I varies from 1 to n for n voltage and resistor, divided by sigma 1 upon Ri. That is the equivalent voltage that we see at point A and B. And then finally, all these resistances are parallel, so we see that an equivalent resistance R equal to, given by 1 upon R equal to 1 upon R1 plus 1 upon R2, all the way up to 1 upon Rn. So this simplified version is a simplified way of calculating the n equivalent resistance, equivalent cells connected in parallel. And then that is what we used up in this formula here. Equivalent potential E is equal to sigma EI divided by Ri divided by sigma 1 upon Ri.